Namaste, everyone, and welcome to the class. You know, your body, it's like its own super specialized pharmacy, constantly mixing up these precise chemical cocktails. And for what? To control one of the most vital things we have, our blood pressure. So today, we're going to go behind the counter of this pharmacy and see exactly how it all works. So, have you ever really thought about it? How does a blood vessel just know when it's time to squeeze tight or when to just, relax? It's not some magic, yar. It's a highly sophisticated, incredibly precise system of chemical signals, and that's what we are going to decode together today. So here's our plan, our roadmap for this session. We'll start with something simple, nitric oxide, the gas story. Then we'll get into the body's own peptide messengers. We'll look at the squeezers, the endothelians, and then the relaxers, the kinins and natriuretic peptides. And then, the most important part for you all, the clinical connection, how we actually use this knowledge to make drugs. A very logical flow, right? Let's get started. Right, first up, nitric oxide, or just NO. Now, don't let that simple formula fool you. This tiny, tiny gas molecule is a real powerhouse in the body. It's a massive signaling molecule, and in the vasculature, its main job is to tell the blood vessels, hey, just relax. It is a super potent vasodilator. And of course, as doctors, we use this knowledge. Imagine a patient comes into the emergency room, hypertensive crisis, blood pressure is through the roof. We need to bring it down, and we need to do it fast. So what can we give? Sodium nitroprusside. Think of it like a little delivery package. It gets into the body and then bam, it releases a whole flood of nitric oxide. The result? Immediate, widespread vasodilation. So simple, but so effective. Okay, so that was the simple gas. Now let's move on to the more complex players in this game, the vasoactive peptides. Just think of these as two opposing teams inside your blood vessels, constantly playing a match. One team's job is to constrict, and the other team's job is to dilate. And here they are, the starting lineups for both teams. On the left, you've got the vasoconstrictors, the squeezers. You've got angiotensin II, vasopressin, endothelins. These are the heavy hitters. And on the right, the vasodilators, the relaxers, bradykinin, the natriuretic peptides, and so on. Your entire cardiovascular health, honestly, is just a constant tug of war between these two sides. It is all about the balance. So let's focus on Team Squeezer first, and we have to talk about their team captain, endothelin. Specifically, we're interested in endothelin 1, or ET1. And guys, let me be very clear. This is the single most potent, the most powerful vasoconstrictor your body can make. It's a huge deal. So how is this supermolecule even made? Well, it's a three-step process, really. It starts out as this big, lazy precursor peptide, prepro ET1. Then it gets a little trim, a snip, and becomes big ET1. But even this one, well, it's not active yet. The real magic, the final step, is when an enzyme called endothelin converting enzyme, or ECE, comes in and makes the final critical cut. And that's what unleashes the active ET1. You must remember ECE. No ECE, no action. Okay, I know this diagram looks a bit intimidating, but trust me, it's very simple. Let's just break it down. Look at the endothelial cell on top. It's making our ET1, right? Now follow that ET1 down to the big smooth muscle cell below. It latches onto two types of receptors there, ETA and ETB. When it binds, it's like flicking a switch. A whole chain reaction starts inside, releasing a flood of calcium. And what does calcium do to any muscle? You know this. It makes it contract. That's the powerful squeeze, the signature move of ET1. But wait, there's a plot twist. This is fascinating. ET1 doesn't only talk to the muscle cell. Look, it can also bind to ETB receptors on the same endothelial cell that made it. And what happens then? This is the crazy part. It actually causes the release of, guess who? Our old friend, nitric oxide, which causes a brief, temporary relaxation. How strange is that? It's like the body gives a tiny relax signal just for a moment before the big, powerful squeeze command takes over. A very neat little feedback loop. Okay, enough about the squeezers. Let's switch sides. Time to meet the other team, the relaxers. These are the guys who fight back, who provide the counterforce to all that endothelin action. They are all about vasodilation and keeping our fluid balance in check. First up for the relaxers is bradykinin, another really powerful vasodilator.
The body makes it on demand, but look at this. It gets broken down almost instantly. Its power is kept on a very tight leash. Now, here's the most brilliant part, something you absolutely must remember for your exams. Look at the enzyme that breaks it down, kinase 2. Does that sound familiar? It should, because kinase 2 is the exact same enzyme as ACE, angiotensin converting enzyme. This is not a coincidence, my friends. This is a beautiful, elegant point of control in our physiology. Next up on Team Relaxer, we have the natriuretic peptides, or NPs. The name itself tells you everything. Natri for sodium, uretic for peeing it out. So their job is to get rid of sodium in the urine. Simple. So when does the body use them? Well, when your heart muscle gets starched out, like a balloon that's too full, because of high blood volume, it releases these peptides. ANP from the atria, BNP from the ventricles, and their one and only job is to relieve that pressure. And this diagram? This shows the whole system in all its glory. It's beautiful, really. When the heart releases these NPs, they launch a two-pronged attack. First, they directly relax the blood vessels and tell the kidneys, get rid of sodium and water now. But at the same time, look, they actively hit the brakes on the entire RAS system. This is the key takeaway, okay? The natriuretic peptide system is the body's own natural built-in antidote to the RAS system. One pushes up, the other pushes down. Perfect balance.
Okay, enough theory. Let's get to the practical stuff, the clinical connection. This is why we learn all this, right? To see how we can use this knowledge in the real world, in the clinic. Because if you understand the pathway, you can design a drug to block it or to boost it. So, let's take a case. Pulmonary arterial hypertension, or PAH, a very serious condition where the blood pressure in the arteries of the lungs goes dangerously high. And in many of these patients, what do we find is the culprit? An overproduction of our friend, the super squeezer, ET1. The balance is totally off. So the target for our therapy becomes crystal clear, doesn't it? We have to block ET1. So, how do we block ET1? Well, we block its receptors, and we have two main strategies. One way is to use a drug like bosentan, which is a dual antagonist. It blocks both receptors, ETA and ETB. Just blocks everything. But then there's a smarter approach, you could say. Drugs like ambrisentan are selective. They only block the ETA receptor, the main one that causes all the constriction. And the theory is, by leaving the ETB receptor free, we can still get that little bit of helpful vasodilation from nitric oxide. Clever, no?
Okay, pay attention now. This is 5-star, high-yield stuff for your exams. Side effects of these drugs. Think logically. You are causing vasodilation, so you'll get headache, flushing. Makes sense. They can also cause some fluid to build up, so you get peripheral edema. Very important, they can be hard on the liver, especially bosentan, so you must monitor liver function tests. And the biggest, most critical point, they are teratogenic. They can cause severe birth defects. So they are absolutely 100% contraindicated in pregnancy. You must remember this. Now let's look at a totally different way of thinking. A new frontier, really. Instead of always blocking the bad guys, what if we could help the good guys? What if we could boost a helpful pathway? That's exactly the idea behind drugs like sacubitril. So you remember our helpful natriuretic peptides, right? Well, there's an enzyme called neprilysin, or NEP, whose only job is to break them down. Sacubitril comes in and blocks that enzyme. It's like telling the bodyguard of the good guys to take a coffee break, so our own NPs can hang around for longer and do more of their good work. And did it work? Oh my goodness, did it work? The results were absolutely game-changing. There was a huge trial, the Paradigm HF trial, and it showed that combining this new drug with an ARB was 20% better at preventing death or hospitalization in heart failure patients compared to the best drug we had at the time. This wasn't just a small step forward, this was a giant leap, a massive breakthrough, all because we understood these peptide pathways. So after all of this, what's the big picture? What's the main takeaway message I want you to remember? It's this. The whole cardiovascular system is just a constant, delicate balancing act. It's a nonstop tug of war between these super powerful constrictor peptides and the dilator peptides. And almost every time you see a cardiovascular disease, it's just a story of this perfect balance being broken. And that brings me to my final thought for you all. We've figured out how to target endothelians, we've figured out how to boost natriuretic peptides, but this internal pharmacy of ours is huge. It's full of secrets we haven't even discovered yet. So the real question, the one I'm leaving for your generation to answer is, what's next? What other messengers are out there waiting to be found? The next big breakthrough drug is just waiting for one of you to discover it. Thank you.
Hello, everyone, and welcome. Today, we're going to dive into a really fascinating topic in medicine. We're going to explore the world of these tiny molecules inside our bodies, and we'll see how understanding them is absolutely revolutionizing how we treat diseases. Believe me, this is where modern medicine truly begins. So, let me start by asking you a question. Think about three very different, very serious problems. First, those terrible, debilitating migraines. Then, that awful nausea that patients get after chemotherapy. And finally, a failing heart, congestive heart failure. Now, on the surface, what do they have in common? They seem completely unrelated, no? But what if I told you there's a single thread connecting them all, right down at the molecular level?
And there you have it. The answer is right there, at the molecular level. You see, each of these conditions, they are all being driven by very specific molecules. And the beauty is, once we identify these molecules, once we know who the culprit is, we can design medicines to target them precisely, incredibly effective treatments. This idea, this is the whole foundation of modern pharmacology.
All right, then, let's put on our detective hats, shall we? We are going to investigate some of these key molecular players. We'll find out what trouble they're causing, and most importantly, we will see how modern medicine has designed a way to catch them and stop them in their tracks. So our first suspect, and it has such a dramatic name, no? Substance P. Now, what is this substance P? You can think of it as the body's alarm system. The moment something goes wrong, an injury, some inflammation, anything bad, substance P is right there, one of the first responders on the scene shouting, "Emergency, emergency." Okay, so what is it exactly? Technically, it's a neuropeptide, but let's simplify that. Just think of it as a small protein that acts like a postman in our nervous system. And what messages does it carry? Well, it's the main messenger for pain signals, for starting inflammation, and this is very important for our story today, for causing that feeling of nausea. And what's really fascinating is just how many jobs this one molecule does. It's a real multitasker. It carries pain signals all the way up the spinal cord, it helps create inflammation, and it is a powerful trigger for the vomiting centers in the brain. Now, this last part is absolutely critical. Why? Because this is a huge reason why cancer patients suffer from such terrible nausea after chemotherapy. And this brings us to the beautiful part. You see, when you understand the mechanism, you can find the solution. So, how does substance P cause all this trouble? It has to bind to a specific gate or receptor. In this case, it's called the NK1 receptor. The logic then becomes very simple, isn't it? If we can just block that gate, block that receptor, then substance P can't deliver its message. And if the message isn't delivered, the nausea doesn't happen. And that is exactly what we did. We developed clever drugs called NK1 receptor antagonists. A very good example is a drug called apripitant. What does it do? It's designed to just go and sit in that NK1 receptor, occupying the space. It's like putting a key in the lock so the wrong key can't get in. And by blocking substance P, it gives tremendous relief to patients. A perfect, beautiful example of targeted therapy. Now, let's take this same idea, this principle of targeted therapy, and apply it to another problem. Our second molecule is CGRP. The full name is calcitonin gene-related peptide, but CGRP is fine. For the millions and millions of people who suffer from those awful migraines, CGRP, this little molecule, is public enemy number one. So how does this CGRP start all the trouble? Well, think of it like a series of dominoes falling, a cascade. It starts when the trigeminal nerves around the brain release a flood of CGRP. What happens next? This CGRP makes the blood vessels in the brain's protective covering, the meninges, swell up and start to leak. This leaking fluid causes inflammation, and this whole messy process is what triggers a full-blown, debilitating migraine. And this is where we see a huge jump forward in how we treat migraines. See, before, what did we have? Just general painkillers, right? They only tried to numb the pain after it had already started. But now, because we understand CGRP's role, we have targeted blockers. These are not just for the symptoms, no. These drugs can stop that whole domino cascade from even beginning. It's prevention, not just a cure. So how do we do it? With amazing precision. We use something called monoclonal antibodies. A good example is aranumab.
Now, don't get scared by the name. These are simply proteins that we create in a lab, and we design them to do one and only one job. Go find the CGRP receptor and block it. That's it. They act like a shield, you know? They prevent the migraine before it even gets a chance to start. For patients, this is absolutely revolutionary.
All right, for our final case today, let's look at an old friend, a truly brilliant medicine called digoxin. This one is all about the heart, and its story is wonderful because it connects our modern molecular science with medicine that comes from ancient plants.
Just look at this molecule. It's what we call a cardiac glycoside. And where does it come from? From a beautiful plant called the foxglove. For hundreds of years, people knew that tea made from this plant could help with something called dropsy, which we now know is the swelling, the edema you get from heart failure. But it took a long, long time for us to figure out exactly how this molecule was working its magic on the heart. So, what's the problem digoxin is trying to solve? Well, in congestive heart failure, the heart muscle, it just gets tired and weak. It can't pump with enough force. And if it's not pumping properly, blood doesn't go where it needs to go, and you get all the symptoms of heart failure. The heart needs help. It needs a boost. It needs to squeeze harder. Okay, now I know this diagram looks a little complicated at first glance. Don't worry, don't worry. The idea behind it is actually very simple, very elegant. This picture is showing us what digoxin is doing inside just one single heart muscle cell. Let's break it down together, step by step. So, here is how it works. Ready? Step 1, digoxin comes along and blocks a very important pump in the cell, the sodium-potassium pump. Step 2, now that the pump is blocked, sodium ions can't get out, so they start to build up inside the cell. Step 3, this extra sodium inside has a knock-on effect. It causes calcium ions to also start building up inside the cell. And step 4, this is the magic step. In any muscle cell, what is the trigger for contraction? It's calcium. So more calcium means a stronger squeeze, a more forceful heartbeat. So simple, so elegant, and so powerful. And this graph, this shows you the result perfectly. You see that green line? That's our weak, failing heart, not doing so well. But now look at the blue line. This is the heart after getting digoxin. See that? The heart's performance, what we call its stroke volume, is boosted so much. It's getting much, much closer to the normal, healthy heart, which is that red line. This is the proof. This is what that clever molecular trick actually achieves for the patient. Okay, so let's wrap this up. We've talked about nausea, we've talked about migraines, we've talked about heart failure, and through it all, I hope you've seen one big idea, one common theme coming through again and again. And the main takeaway message, the thing I really want you to remember, is this. The entire foundation of modern medicine is built on this one simple, powerful idea. If you can understand the molecule that is causing the problem, you can design a medicine to fix that problem. It's that simple. That is the journey we take, from the science in the lab to the medicine that helps the patient. So, I will leave you with a final thought. By targeting these tiny, tiny molecules, we have made such incredible progress, haven't we? So the question is, what's next? Where do we go from here? Could this be the way we finally tackle something like Alzheimer's, or autoimmune diseases, or even the cancers we still struggle with? The entire future of medicine, my friends, will be built on finding the answers to these questions. Thank you very much.